In this video, we're going to start talking about the graphs of vectors. And let's start this by talking about what we mean by standard position. Standard position is when your initial point of your vector is at the origin. Now, it's much easier to work with when we graph these things in standard position. And honestly, it's going to look a lot like an angle in standard position that we've been graphing for the past couple of chapters. Okay, component form. If a vector v is in standard position with the terminal point at AB, then the component form is. Now let's talk a little bit about component form. In the last section, we gave you an initial point and we gave you a terminal point. The terminal point is where it stopped. Well, if we're in component form, honestly, when we're in the standard form, our initial point is always 0, 0, so we don't have to list that because we know where we're starting from. So therefore, if the terminal point is located at AB, then that component, what we're going to call component form of vector v, it looks like this. We put our A and B instead of in parentheses, which that looked bad. Let's try that again. We put our AB in these vector symbols. So that would be the component form because we know when we see that we're starting at the origin and we're stopping here. That's the terminal point. The magnitude and direction of a vector can be found using the following formulas. Okay, the magnitude, again, is simply Pythagorean theorem. However, think about this. It's a little bit easier now because we don't have to find that distance anymore. This will be A, this will be B. So therefore, the magnitude of vector b will simply be the square root of a squared plus b squared. So we don't have to find that distance anymore. So it looks very similar. And then the direction angle, just like from last chapter, we know that the tangent of our direction angle will equal opposite over adjacent, which will be b over a. Now, you do have to be careful again because you might be, that would give you your reference angle. So if you're in a third or fourth quadrant, you might have to do it a little bit different, or second or third quadrant, excuse me. So let's find the magnitude and the direction of each of these vectors. So number one, vector r, and you can sketch out a graph of this if you'd like to. 7, 24, so go right 7 and go up 24. It's going to be located somewhere up here. Just get a decent sketch of it. Doesn't have to be exact. So therefore, sketch yourself a little right triangle. So this is 7 and this is 24. So therefore, the magnitude can be found by and let me do the symbol. The magnitude of vector r can be found by the square root of 7 squared plus 24 squared, which would equal the square root of 625, which is 25. So there's your magnitude. Now let's find direction. We know that the tangent of my reference angle, and that's actually what we're looking for here is the reference angle, would be opposite over adjacent, which is 24 over 7. So let's do the inverse tangent of 24 over 7, and we get an angle of 73.74 degrees. So therefore, there is your magnitude and direction. Same thing. So for now, we're in the third quadrant. -3, -1 would be somewhere down here. So the direction is going to be a little bit tougher, but the magnitude is the exact same thing. Let me put an arrow on it so it's a vector. So the magnitude of vector n is equal to the square root of a squared plus b squared, which is square root of 10. And that's going to be somewhere a little bit bigger than 3. So you could write it as exact, or you can write it as about 3.16. And then finally, direction. We know that, let's find our reference angle first. Draw yourself a little right triangle. This is 3, this is 1. So therefore, the tangent of my reference angle is going to be opposite over adjacent. So therefore, theta will be the inverse tangent of 1/3, which is going to be about 18.43. But again, we have an issue because that's not our direction. That's our reference angle. So we have to tack this onto it. So that'll be 180 more. So your actual reference angle, your actual angle there would be 198.43 because it is a third quadrant angle. Okay, number 3. Again, magnitude first. The magnitude here of vector v will be the square root of a squared plus b squared. That's going to be the square root of 208. And that does simplify. We can break that into the square root of 16 times the square root of 13. So there's your magnitude, and that's going to be approximately 14.42. So there's your two answers for magnitude. Now direction, let's see, we're going right and down. So this is quadrant 4, so you got to be careful with that. So our reference angle again, we know that the tangent of theta will be opposite over adjacent. So that's going to be 12 over 8. We're going to do this just to find our reference angle. So we're going to do the inverse tangent of that. You don't have to reduce it or anything. And you're going to get for theta 56.3 degrees. And again, I can't stress this enough. I don't worry about positive negatives. If you'll completely drop the positives or completely drop the negatives, that gives you your first quadrant reference angle. And then to me, it's a whole lot easier to figure out, okay, if 56.3 is my reference, that would be this angle. In order to find out what this fourth quadrant angle is, just simply subtract that from 360, and you're going to get that your reference angle is going to be, you're going to get your directional angle is 303.7 degrees. Number 4, negative 11.6. That puts you in the second quadrant. Your actual magnitude is going to be the square root of a squared plus b squared. That's going to be the square root of 157, which is going to be about 12.53. So there's your two answers for magnitude, the exact and the approximate. Next up, let's find our reference angle to begin with. We do so by doing opposite over adjacent, or b over a, so 6 over 11. When you do the inverse tangent of that, that gives me a reference angle of 28.61. But again, that's my reference angle. Look back, and you are actually in the second quadrant. So you're looking for what angle in the second quadrant has a reference angle of 28.61. So simply subtract from 180, and that gives you that your directional angle is equal to 151.39 degrees. Number 5. -2, -8 is a third quadrant point, or a third quadrant vector here. So first off, let's find our magnitude. The magnitude of vector G is going to be the square root of a squared plus b squared, which will be the square root of 68. And I believe that reduces to the square root of 4 times the square root of 17. So 2 root 17, which is going to be about 8.25. So there's your exact and approximate magnitudes. Next up, let's find direction. I know that the tangent of my, again, reference angle will be opposite over adjacent. That'll be 8 over 2, or -8 over -2, which is 4. So we're going to do the inverse tan. Theta will be the inverse tangent of 4. And that's going to give me theta is equal to an angle of 75.96 degrees. And again, that's my reference angle. I'm looking for a third quadrant angle whose reference angle is 75.96, which is somewhere down here. So I've got to do 180 plus the 75.96. So my angle is going to be 255.96 degrees. Okay, number 6. Again, magnitude of vector A will be the square root of a squared, which is 196, plus b squared, which is 25. That's going to be the square root of 221, which is about 14.87. So there's exact and approximate. Next up, we know that the direction, the tangent of our angle theta, is going to be opposite over adjacent, or b over a. So therefore, the inverse tangent of 5 over 14 gives me an angle of 19.65 degrees. And we're actually looking for a first quadrant angle, so my reference angle is sufficient. Okay, in this next part, we're going to be writing vectors in component form. If you're given the two endpoints, you're given the initial point and you're giving the terminal point, how do you write that in component form? And it's really super easy. Any vector with an initial point x1, y1 and a terminal point x2, y2 can be written in component form as follows. Vector v, that vector will simply be x2 minus x1, comma, y2 minus y1. You simply subtract the x's and you subtract your y's. Subtract the terminal point minus the initial point, and you've got your vector in component form. So it's really easy. So starting with number 7, let's write CD in component form. So vector CD will equal, simply subtract your x's first. 6 minus 3 is 3. Subtract your y's and you get -2. There it is in component form. So pretty much you have moved it from where it was to the origin with that simply subtracting them. Vector RS here, written in component form. Again, simply subtract your x's. -2 minus 5 gives you a -7. Subtract your y's. 1 minus 10 gives you a -9. That is the exact same vector with its initial point at the origin. Okay, next up, number 9. Give the component form, the magnitude, and the direction of each vector. Okay, let's start with the component form. Find component form, subtract your x's. 4 minus 2 gives you 2, comma. 1 minus -9 gives you 10, so there's your component form. To find the magnitude, you do the square root of a squared plus b squared, and again, I'm using the component form to find that. You could have done it either way. You could have also used Pythagorean theorem here. It has the same magnitude, so that's going to be the square root of 104, which we can simplify. That's going to be the square root of 4 times the square root of 26, so 2 root 26, or you can write that as a decimal. And then finally, the direction angle. And again, I'm using this component form to find our direction angle. So 210, you are in the first quadrant, so go over 2, up 10. It's going to look something like this. The tangent of tangent of your reference angle will be b over a, or 10 over 2, which is 5. So to find the actual theta, do the inverse tangent of 5, and you get 78.69 degrees. So that's going to be your angle of direction. The second one, your component form, again, subtract your x's. X2 minus x1, -4 minus 9 is a -13. Subtract your y's, -1 minus -3, that's -1 plus 3, which will be 2. So there's your component form. Magnitude will be the square root of a squared plus b squared. So that'd be the square root of 173, and I do not think that simplifies, but you could give that in decimal form as well. And then finally, let's find our direction. Let's see, -13.2, that's going to be a third quadrant angle. So let's first find our reference angle. I know that the tangent of theta, and again, I disregard all negatives, will be b over a, so 2/13. When you do the inverse tangent of 2/13, you get a value of 8.75 degrees. But again, we have to keep in mind that's in the third quadrant. So that's our reference angle. So you're going to have to do 180 plus that. So our angle of direction will be 188.75 degrees. Number 11, same thing. Component form, x minus x will be 6. Y minus y gives you -7. The magnitude will be the square root of a squared plus b squared, which will be the square root of 85. And I do not think that simplifies, but you could, again, write the decimal form. The tangent of my reference angle will equal b over a. Again, disregard the positives and negatives. So its tan is 7 over 6. So therefore, that tells me that theta would equal 49.40 degrees. Since we are in the, let's see, that would be the 6, -7. That's a fourth quadrant angle. So in order to actually find the angle, my reference is 49.40. So I'm going to have to do 360 minus that. And that gives me a direction angle of 310.60 degrees. Number 12. Now this one, they actually gave me a graph of this vector. So what I'm going to have to do is take the 2 points. My initial point is -1, 4. My terminal point is 1, 2, 3, 4, 1. So therefore, component form is going to be x minus x will be 5. Y minus y is -3. Now, I do want to graph this just to show you something. 5, -3. 1, 2, 3, 4, 5. 1, 2, 3. If I were to graph that, draw that vector, I do want you to see that it's identical to this vector. It's the exact same vector that's just been moved into standard form to where its initial point is at 0, 0. So now the rest of it's easy. Magnitude is simply Pythagorean theorem. That's going to be the square root of 25 plus 9, a squared plus b squared, which is root 34, which is going to be somewhere between 5 and 6. The direction angle, it's a fourth quadrant angle. So therefore, we first find our reference angle. I know the tangent of theta would be 3/5, b over a. So that gives me a reference angle, which is actually going to be this angle right here of 30.96 degrees. So therefore, in order to find this angle, which is what we're looking for, we're going to do 360 minus that, and that gives me a direction angle of 329.04 degrees. Next up, we're going to be talking about more with equivalent vectors, a little bit more talk about equivalent vectors. It says vectors are equivalent if and only if, again, they have the same component form. They have the same direction, the same magnitude. So if they're written in component form, they would have to have identical component forms. So use component forms to determine if these are equivalent. So all we're doing here is we're going to write each of these in component forms. So let's start with AB. And let's do, again, x minus x, y minus y, -7 minus -3, that'd be a -4. -2 minus 6, that'd be a -8. That would be vector AB. Now let's do vector CD in component form. We're going to do x minus x, -1 minus 3, which is -4. -9 minus -1 will be -9 plus 1, which is -8. And notice they have the same component form. So are they equivalent vectors? Yes, they are. Even though they have different starting points and different ending points, when written in component form, they're the exact same vector. Number 14, let's start with vector AB. X minus x, 0 minus -9 gives you a value of 9. -8 minus -2 is -8 plus 2, which gives you a value of -6. Vector CD. X minus x, 4 minus -5 gives me a value of 9. 8 minus 2 gives you a value of 6. So 9, -6, and 9, +6 are not equivalent vectors. Now, if you were to test the magnitudes would be the same. However, the directions are going to be different. So therefore, no, these two vectors are not equivalent.